Okay, so I should start by thanking the organisers for putting on this lovely event and for giving me the opportunity to speak. I'm sorry that I didn't get to see Bracelet Bay in person, but hopefully sometime in the future. I guess I'm a little bit of an outlier here because my route into skew braces hasn't really didn't start with the Yang-Baxter equation. My background is in Hopf-Galois theory, like Nigel and Andrew, and so I've come into skew braces by that kind of route. Usually, I find myself talking in events where the Hopf-Galois aspect is well known, and the skew brace aspect perhaps a little bit less so. And this time, I guess it's the other way around. So I've included quite a bit of background about the Hopf-Galois stuff. I hope that doesn't end up being boring or patronizing, and I apologize to the experts. Okay, so what I'd like to talk about is some details of the connection between skew braces and Hopf-Galois structures on Galois field extensions, and I suppose the real meat of what I'm going to talk about is how you can use skew braces to tell you something about these Hopf-Galois structures. As I say, that's kind of the way that I came into this. So I'm interested in how kind of structural properties of these objects are connected to each other, and what you can learn about a particular Hopf-Galois structure by the corresponding skew brace. So as I say, the first few points here are kind of background type material. I'll give a quick overview of some of the definitions and some of the applications, why you might care about these things. And then the second and third bullet points are the sort of mechanism that links Hopf-Galois structures with skew braces. And then the final 3 points here are sort of some sort of original stuff, some research level stuff, and most of that is joint work with Alan Koch from Agnes Scott College. So I'd like to say something about how skew braces can tell us something about the Hopf-Galois analogue of the Galois correspondence, and how they can tell us something about certain isomorphism problems that crop up in the context of Hopf-Galois theory. I can't see the title of my slide. There we go. Starting with the definitions then, a Hopf-Galois structure on a finite extension of fields is some way of trying to generalize classical Galois theory on a Galois extension. So specifically, what we need, if my field extension is L over K, then I should be looking for a K Hopf algebra and some sort of action of this Hopf algebra on my top field L. So L is an H module, and then it needs to be an H module algebra. So the module action of H on L needs to interact with the structure maps on H in some sort of reasonably nice way. So specifically, if I act on the unit element of my field L, then I should get the co-unit of H multiplied by 1. And if I act on a product, then I can't highlight this second bullet point. If I act on a product of elements in L, then I should get some formula based on the co-multiplication, the various components of my element H here in my Hopf algebra. So those first 2 bullet points are just saying that L should be an H module algebra. And then the third bullet point is this kind of Galois type condition, this non-degeneracy condition that says by the time I tensor extend scalars up to L tensor H, I should basically get all the K linear endomorphisms of L. So specifically, this map J here ought to be a bijection. And the sort of standard example is if I actually do take a Galois extension of fields with Galois group G, then I can obviously build the group algebra KG. That's a Hopf algebra, and that satisfies all of these conditions. That's the prototype for a Hopf-Galois structure on a field extension. Why would you care? Well, one reason you might care, and one reason I'll come back to later on, is it gives you analogues of the fundamental theorem of Galois theory in situations where it might not have been available before. So there's a sort of a notion of a fixed field here. So if I've got H giving a Hopf-Galois structure on some finite extension L over K, if I start with a sub-Hopf algebra, a Hopf sub-algebra, I suppose, if I start with a sub-Hopf algebra H prime of H, I can build this fixed field. I've put fixed field in inverted commas, but it's the sort of analogous thing. So I ask for all those elements of L on which H acts as trivially as possible. H acting on T should be just the co-unit of H multiplied by T. And I ask for that to work for all H in H prime. And that's the fixed field associated to this Hopf subalgebra. So if I start with a Hopf subalgebra, then I can get an intermediate field, and there's some nice familiar sort of index type or dimension type calculations going on here. So the degree of L down to L fixed by H prime is the dimension of the Hopf subalgebra that you first thought of. So that's the analog of the usual fact from Galois theory about subgroups. What isn't always true is that this thing is usually not surjective. This correspondence usually doesn't pick up all of the intermediate fields. If I start with a sub-Hopf algebra, I get an intermediate field, but I shouldn't usually expect to get them all. And it's interesting to try to determine the image of this correspondence in various cases. So Lindsay Childs has quite a recent paper looking at the sort of proportion of intermediate fields that you pick up in a variety of different cases, and perhaps in sort of specific concrete examples you might literally want to know exactly which intermediate fields crop up. If you've got a particular extension and a particular Hopf-Galois structure in mind, you might care about precisely which fields get picked up. So again, if I relate this back to the classical Galois situation, then this is just rephrasing classical Galois theory. The sub-Hopf algebras of Kg are precisely the things that look like Kj, with J a subgroup of G. And so in particular, you can see here that if I take the fixed field in this Hopf-Galois sense, I take the fixed field of the sub-Hopf algebra Kj. That's just the same as asking for the fixed field of the subgroup J from classical Galois theory, and the dimension statement that I gave here in the second bullet point drops out immediately. So another reason why you might care about Hopf-Galois structures, so this is very sideways from this conference, but another reason why you might care about Hopf-Galois structures is they give you contexts for studying integral module structure, for asking questions in algebraic number theory. So if I'm particularly looking at a Hopf-Galois structure on an extension of local or global fields, then I can study the ring of integers, the valuation ring, any fractional ideal I like, relative to that Hopf-Galois structure by forming this associated order. So I take the subring of H that is all those elements of H that map my fractional ideal back to itself, and that turns out to be an order in my Hopf algebra H, and I can study the structure of my fractional ideal relative to, as a module over this order. And so that gives, there's lots of opportunities to chop and change there. If you've got a particular fractional ideal, or perhaps you're particularly interested in the ring of integers, you might chop and change the different Hopf-Galois structures and ask yourself whether one of them gives a better description than the others, or if they're all equally good. And it gives you context for asking these kinds of questions where the techniques of classical Galois theory are not available. You can try this on non-normal or inseparable extensions. Having said that you can try it on non-normal or inseparable extensions, some of the most interesting results here are for extensions that are already Galois. One of Nigel's, I think it's fair to say, one of Nigel's very famous results now is he created some families of extensions of p-adic fields, which are Galois in the classical sense, and also Hopf-Galois for a different Hopf algebra. And the ring of integers is not free over its associated order in the classical setup, but it is free over its associated order for some other Hopf algebra giving a Hopf-Galois structure. So as I say, this is kind of sideways to the thrust of this conference, but this is one of the major reasons that I'm interested in this kind of thing. So that's why you might care about Hopf-Galois structures, and particularly why you might care about Hopf-Galois structures on Galois extensions, even though one of the points is that you can do some kind of Galois theory on non-Galois extensions. There's plenty of motivation for using these things or studying these things in the context of extensions that are already classically Galois. And if you want to do that, then there's a machine for actually crunching out the Hopf-Galois structures in a particular case. So I imagine that I'm afraid I didn't see Andrew's talk on Tuesday, but I imagine that this Greiter-Paragus theorem was already mentioned by Andrew on Tuesday. But let me just give a high-speed recap in the Galois case. I guess Andrew wasn't doing the Galois case. Let me just give a high-speed recap here. So what I'm thinking is that I'm looking at a Galois extension L over K with Galois group G, and what I'd like to do is to crank out all of the Hopf-Galois structures on this extension. I'd like to try and enumerate them. I'd like to try and describe the Hopf algebras that are involved. And the setup for doing that starts with the group of permutations of G and this left regular representation of G into its own permutation group. And I want to use that left regular representation to let G act on its own permutation group by the formula given here. So an element G of G acting on a permutation eta is just going to be eta conjugated by lambda of G. So lambda of G sits in the permutation group. This at least makes sense. So that gives me an action of G on perm G. And then it turns out that in order to enumerate the Hopf-Galois structures on my extension, what I ought to do is to try and enumerate the subgroups of perm G that are regular on G and stable under this action. So another language would be to say normalized by lambda of G, normalized by the image of the left regular representation. So this theorem of Greiter and Paragus tells you that there's a bijection between those subgroups and these Hopf-Galois structures that you want. And more than that, you can build the Hopf algebra that's acting. So if you've got one of these subgroups N, you form this group algebra Ln, so that's an L Hopf algebra, and then you take fixed points under a certain action of G. So you let G act on this group algebra by acting on L as the Galois automorphisms, acting on N via this formula in the third bullet point. And it certainly will act on N because we've insisted that N should be stable under this action. So G really does act on N. And then I take the fixed points of Ln under that action. And by Galois descent, I get a K Hopf algebra. It has the correct dimension at least. And you can then show that it does give a Hopf-Galois structure on this extension. And it comes in the Greiter-Paragus theorem, it comes sort of packaged with a particular action. So if I think of N as a particular subgroup, it comes sort of packaged with a particular action of that Hopf algebra on the extension. And just for future reference, I'll be using this term type. So the isomorphism class of N is the type of the corresponding Hopf-Galois structure. So we can talk about cyclic type, abelian type, simple type, whatever. So let me just whiz through a couple of examples. I'm sure these are pretty familiar. So as a reminder that for my fixed group G, which is supposed to be the Galois group of my extension, I'm after G stable regular subgroups. Well, I suppose the most natural place to start would be lambda G itself, but I'll do that second. The place I'm going to start is rho of G, the image of G under the right regular representation. And then because the elements of lambda of G and the elements of rho of G commute inside the permutation group, G acts trivially on rho of G. So when I take the fixed points of L rho of G, that L Hopf algebra, the action of G on the group elements rho of G is trivial, so it just sort of slips past, and all I end up doing is fixing the coefficients. So I get K of rho of G, and I said this comes packaged with a sort of prescribed action, and if you chase through that action, it's just the classical Galois action. And so this is the classical Hopf-Galois structure. This is the Hopf-Galois structure you get from normal Galois theory showing up in this Greiter-Preiris classification. So perhaps a slightly more interesting thing is to look at lambda G itself. If G is abelian, I don't get anything new this way. But if G is non-abelian, then this is a distinct, interesting regular subgroup. And in this case, the orbits of G in lambda of G are just the conjugacy classes. And so when I take the fixed points, you get something a little bit more interesting happening. You don't get the same Hopf algebra. And this thing has been, the Hopf algebra you do get has been called the canonical non-classical Hopf-Galois structure, or the standard non-classical Hopf-Galois structure. Whenever G is non-abelian, this thing is available. And then just one more concrete example. This is going to be sort of a running example through this talk. It's pretty small, but this sort of construction extends to a much larger family. If I take a D3 extension, then I can cook up a Hopf-Galois structure of cyclic type. And there's this nice sort of construction where I do a sort of a combination of something from lambda of G and something from rho of G. So here, if I take eta to be lambda of R, rho of S, then again, because the elements of lambda of G and rho of G commute with each other, that ends up having order 6. And so I take N to be the cyclic subgroup generated by that eta. That thing has order 6, and you can check that it's regular and that it's G stable. The action of G is pretty simple. So there I get an example where the N is cyclic, but the original Galois group is dihedral. And then, so then I think that the route to the link with braces goes through another one of Nigel's results, which I think originally was aimed at trying to make the search for these regular subgroups a little bit more tractable. And so instead of doing this sort of search for regular subgroups of the permutation group, there's this idea of reversing the roles of N and G in some sense, and that ends up making the computations a lot easier. So this requires a slight change of perspective. I've been thinking about N as actually being a regular subgroup of perm N, and just for now I want to step away from that a little bit, let N be an abstract group of the same order as G, and because I'm heading in a brace kind of direction, I want to label the binary operation on N. So the binary operation that N starts out with, I'm going to write as star. And then Nigel's so-called translation theorem says that there's a bijection between these two sets of regular embedding. So a regular embedding is an embedding whose image is a regular subgroup. So the things in this set curly N are close to what I want. I'm interested in certain special regular subgroups of perm G. So the things in this set curly N have images that I'm interested in. And then the theorem says you can flip this around, and there's a bijection between the regular embeddings in that set and the regular embeddings in this set curly G. But of course, we don't just want any regular subgroups of perm G, we want these special ones, and that's what these bullet points at the bottom here tell us about. So I'm particularly interested in those alphas for which alpha of N is G stable, and that happens if and only if the corresponding beta from G into perm N actually lands in the holomorph of N. So I want to think of the holomorph I'm just sort of simultaneously, kind of sloppily, thinking about the holomorph as being parked inside the permutation group. So think of it as lambda n aut n sat inside the permutation group. But I also want to remind myself that I can think of it as the semi-direct product of external semi-direct product of n and aut n. So the first bullet point there says that tells me when something in the first set is G stable. And then because I'm dealing with embeddings, there's always this possibility that two embeddings could have the same image. And the second bullet point tells us when we can detect that two of these embeddings, alpha and alpha prime, have the same image if and only if the corresponding beta and beta prime are conjugate as maps by some element theta in aut n. So the actual, I want the actual maps to be conjugate, not just their images as sets. So instead of asking about regular subgroups of perm G that are G stable, I can ask for regular subgroups of the holomorph of N that are isomorphic to G, and then chase that information back. So, as I say, for years, this was used as a way to simplify the enumeration of Hopf-Galois structures on a given Galois extension, because it gives you a much smaller group to search through. But sort of relevant to this conference, it reveals the connection with skew braces. So if I've got one of these embeddings from the second set, I've got a regular embedding beta of G into hol n, then if I just act on the identity element of n, that gives me a bijection from G to n, and I can use that bijection to impose a new binary operation on n, which I'll call circle, and then n with circle is isomorphic to G. So now I've got n with two binary operations on it, and using the fact that beta of G actually lands in the holomorph, n with its original binary operation star and its new binary operation circle is a skew brace. I'm well aware that I'm teaching you all to suck eggs at this point. And then we can obviously run the whole thing in the other direction. If I start with a skew brace, then from that I can build a regular subgroup of hol of B star that's isomorphic to B with circle, and that's going to yield at least one Hopf-Galois structure. And the way the pieces fall out is it's going to give me a Hopf-Galois structure of type B star on a Galois extension with Galois group B circle. And I say at least one, so I'll make this a little bit more precise in a moment. So precisely what I need to do is, if I'm given two groups G and N of the same order, if I'm after Hopf-Galois structures of type N on a Galois extension with Galois group G, then I should be looking at regular embeddings of G into hol N up to this equivalence given by conjugation of the actual maps. B prime should be a conjugate of beta. And if I'm interested in skew braces with B star isomorphic to N and B circle isomorphic to G, then I should be looking for regular subgroups of hol N that are isomorphic to G up to a different notion of equivalence, this notion of equivalence as sets rather than at the level of this actual embedding. So there's certainly a surjection from the set of Hopf-Galois structures to this set of skew braces, but teasing out the exact these different equivalences is not totally straightforward. Because I came at this topic from the Hopf-Galois kind of side, I always have an inclination to think about or to think about skew braces in the perm G kind of context, the sort of the left-hand side of the translation theorem, if you like, the Greit-Paraigis kind of side of the translation theorem. And it's perfectly possible to write out all the details and to connect Hopf-Galois structures with skew braces directly in the perm G setting. But I get the sense that that's less familiar to people who started with braces. But I'll come back to that later on. So what happens if you play this game? In some of the cases that I've already looked at, So if for the time being, if I assume that n and g are isomorphic, and I sort of fix an identification of n with g, then I can look at embeddings of n into its own holomorph. So one thing I can do is this sort of right regular representation. So beta of eta hitting pi is pi eta inverse, and that turns out to have regular image and land in the holomorph. And if you translate back again, then you get rho g, which corresponds to the classical Hopf-Galois structure, the kind of I don't want to say trivial, but the original, the classical Hopf-Galois structure. But if you chase through the circle operation that you get from this kind of construction, you don't get the trivial skew brace, which was a surprise to me when I started thinking about this kind of thing. You get what Alan and I have been calling the almost trivial skew brace, where the circle operation is just the reverse of the star operation. And then sort of symmetrically, if you, oh, I'm sorry, I've got a star in one of these and not in the other, but suggestive enough. If you do left multiplication, if you define your map beta to be left multiplication by eta, then translate back to perm G, you get the subgroup lambda of G, and that corresponds to the standard non-classical Hopf-Galois structure, assuming G is non-abelian. But of course, here you do get the trivial skew brace. So those two sort of notions of trivial and almost trivial are kind of flipped around in these two contexts. And then here's my sort of running example. If G is a dihedral of order 6 generated by R and S, and N is cyclic of order 6, then of course the automorphism group just has order 2, and I can write down a suitable embedding beta G going into hol n. Here's a suitable embedding, and if I translate that back, then I get the regular subgroup, the specific regular subgroup of perm G that I was talking about a few slides ago. And if I play the brace type game, well, there's only one skew brace with star group cyclic and circle group isomorphic to D3, and it emerges like this. I think this sort of formula on the exponents gives you a dihedral structure for the circle group. So there's this kind of circle of ideas centered around these regular subgroups, and with a bijective correspondence with these Hopf-Galois structures, and a non-bijective correspondence to these skew braces. Okay, so as if we hadn't had enough correspondences already, so this is moving away now from the background type material to some stuff which I hope you find a bit more interesting. I mentioned that one of the things you might care about when you're doing Hopf-Galois theory is which of the intermediate fields in your extension show up in the image of the Hopf-Galois correspondence, so the Hopf-Galois analog of the Galois correspondence. And these things correspond to sub-Hopf algebras of H. So not all the intermediate fields are going to occur, but those that do will correspond to sub-Hopf algebras of H. And I just recalled the definition of the sort of fixed field here. But now, from when I stated this previously, I've thrown this Greiter-Pyragis theorem into the mix. So now I know that the H I'm looking at has this particular form. It's the fixed points of a group algebra of this form Ln fixed by G. So what do the sub-Hopf algebras of that thing look like? Well, they look precisely like Lp fixed by G, where P is a subgroup of N that is itself G stable. So it's a subgroup of N, and when G acts on N, P is actually stable under that action. And there's a pretty egregious abuse of notation here. I'm going to write L superscript P instead of L superscript LP fixed by G, and this is very dangerous because the group P is not acting directly. This is really tempting to think this is just like Galois theory, but I don't strictly mean L fixed by P, but the other notation's a bit cumbersome. So in the Greiter-Pyragis context, this is how the sub-Hopf algebras show up, and therefore this is how the interesting intermediate fields are going to show up. Um, and when some of us in the Hopf-Galois community were first aware of the brace connection, which I think largely due to Nigel, when we became aware of the connection with braces, Lindsay Childs asked this question: can you use the associated Skew brace to understand something about the Hopf-Galois correspondence? Well, that is the same as saying, can you use the associated brace to tell you when a particular subgroup is G stable? And he proved this theorem, that he coined this term that said that P should be a circle stable subgroup of the associated brace. So I've got my regular subgroup N of perm G. I'm interested in G stable subgroups of N because they correspond to the intermediate fields that will show up. And then in the context of the brace, what I want is a circle stable subgroup. So it should have this property expressed here. It should be, if I take an element of P and sort of, it's almost like conjugating it by some element eta in N, then that should stay in P. And a consequence of that, I suppose, is that the actual sort of lattice structure of the set of intermediate fields for a particular Hopf-Galois structure only depends on the associated Skew brace. The precise fields you get may wander about, but the sort of the number of them and the lattice structure is only going to depend on the associated Skew brace. So I'm not quite done with the Hopf-Galois correspondence, but it sort of goes hand in hand with this idea of opposite Hopf-Galois structures and opposite Skew braces. So the idea of opposite Hopf-Galois structures has been floating around in the literature ever since Greiter and Paragas's original paper. I think not really under that name, but it's gained quite a lot of interest recently. So if you've got if N is one of these regular G stable subgroups of perm G, then you can take its centralizer in perm G. So you just ask for all those elements of perm G that commute with everything in N, and I'm labeling that N op. And that will be another regular G stable subgroup. If N's abelian, then it's exactly the same subgroup as you started with. If N's not abelian, then this is a new, interesting, regular G stable subgroup. And so it corresponds to a Hopf-Galois structure. And we'll say that that Hopf-Galois structure is the opposite of the one I first thought of. And if you do the construction twice, you get back to where you first started. So we can say they're opposites of one another. And then you can ask the same sort of questions about what happens with the associated braces. So if N star circle is the Skew brace associated to N, then the Skew brace associated to N op is going to be N star prime circle, where star prime just reverses the order of multiplication with respect to star. And so motivated by this, if I've got any Skew brace, I can cook up the opposite of it just by flipping that first operation. So Alan Koch and I came at this idea this way, and we published a paper talking about opposite Skew braces, and our motivation was entirely coming from Hopf-Galois structures. I think at the same time, certainly independently, Rump came up with the same construction by the same name. So it's I think it was introduced to the literature sort of simultaneously by both of us, and he had totally different motivations. So here's some examples. In this kind of language, the regular subgroups rho of G and lambda of G are opposites of one another. I've already used the fact that the elements of these two subgroups commute with each other. So that's saying that the trivial Skew brace on a fixed group G and the almost trivial Skew brace on a fixed group G are opposites of one another. And here's my running example. If my G is dihedral of order 6 and my N is cyclic, well, then there's not a lot to say, because if my N is cyclic, then the Skew brace, the star group of the Skew brace is abelian, and so this thing is self-opposite. It is possible to cook up self-opposite Skew braces where the star group is not abelian, but the only ways I know of doing that feel a little bit artificial at the moment, but they do exist. I certainly don't know how to characterize them, which would be pretty interesting. Okay, so I said I was going to talk about opposite skew bases in sort of tandem with the Hopf-Galois correspondence, and this is why. So Lindsay Childs coined this term circle stable subgroup to characterize the G stable subgroups of N. So let's use the skew brace to characterize the G stable subgroups of my group N, and then they lead on to the intermediate fields in the image of the Hopf-Galois correspondence. But as far as I know, and I think as far as he knew at the time, this construction didn't line up with anything in the skew brace literature. But if you pass to the opposite skew brace, then a circle stable subgroup, if you move over to the opposite skew brace, what you're asking for is this condition expressed at the bottom of the slide, and that looks much closer to something that was already known in the skew brace literature. That looks quite close to asking for P prime to be an ideal of this skew brace, except that there's no particular reason why P prime should be normal with respect to either of the binary operations. So Alan and I called these things quasi-ideals of the opposite skew brace, and then interesting things happen depending on, well, sort of how close P prime is to being a genuine ideal. So I guess the motivation or the slight advantage here is that when you bounce over to the opposite skew brace instead of the original one, this condition that tells you about the intermediate fields in the Hopf-Galois correspondence starts to look a lot more like some familiar substructures of skew brace. So this is a theorem from our paper about opposite skew braces. So this is the setup is just what I've been talking about, a Galois extension with group G. H is some Hopf-Galois structure on N over K. N star circle is the associated skew brace. I'm interested in P being a circle stable subgroup of this thing, which means that when I pass to the opposite brace, it's a quasi-ideal. And then additional properties of P prime tell you quite a lot about that intermediate field. So there's that intermediate field L fixed by P, or by abuse of notation, L fixed by P. So L fixed by P down to K is a Galois extension if and only if P prime is normal in the circle group. It's a Hopf-Galois extension if and only if P prime is normal in the star group, or the star prime group, I suppose. And both of these things happen if and only if it's genuinely an ideal of the opposite skew brace. Point 2 picks up on a sort of another collaborative project from a few years ago, so this was again myself and Alan Koch and Tim Coll and Rob Underwood, and we looked at sort of quotient Hopf-Galois structures. So we were trying to generalize the sort of quotient group parts of the fundamental theorem of Galois theory in the Greit-Paraygis context. If I've got some intermediate field that is in the image of the Hopf-Galois correspondence, then it's always true that I have a Hopf-Galois structure on L down to the intermediate field. And one of the things we were asking is, can you cook up a Hopf-Galois structure on the bottom part of the extension, the intermediate field down to the base field, and trying to express that in terms of Greit-Paraygis theory? Can you identify that Hopf-Galois structure in the context of Greit-Paraygis theory? And it turns out you can. And so the second bullet point here picks up on a lot of that. So when I say L fixed by P down to K is a Hopf-Galois extension, you can construct a or the Hopf-Galois structure on that extension quite explicitly from this kind of information. And interestingly, I mean, we found back then, and it's evident here, you can pick out intermediate fields in the Hopf-Galois correspondence that aren't Galois extensions of your base field, but are Hopf-Galois extensions. So that has implications going back to the algebraic number theory and the sort of generalized Galois module structure, for example. So the Skew brace can tell you all about this kind of stuff. So here's my running example again. So I've got my D3 Galois extension with my Hopf-Galois structure of cyclic type. So my N group here is cyclic. Well, because N with star is cyclic, that means it's got a unique subgroup of order 3 and a unique subgroup of order 2. Basically, by uniqueness, each of those is G stable, and that means that I get these intermediate fields, L, sort of L fixed by P dangerously, and L fixed by Q. And again, because N with star is abelian, each of those is normal. So L fixed by P down to K and L fixed by Q down to K are certainly Hopf-Galois extensions. But if I want to know whether or not they're Galois extensions, I should ask myself what these subgroups look like with respect to the circle group. And of course, in that case, the subgroup of order 2 is not going to be normal. And so L fixed by Q down to K is not a Galois extension, but it is a Hopf-Galois extension. So you can read off quite a lot of information about the properties of these extensions from the associated Skew brace. And if you've got the patience, you can chase the information back through and find out quite concretely what the Hopf-Galois structures on these extensions might actually look like. Okay, so now for something completely different, another class of problems that's attracted a bit of interest in recent years are certain isomorphism problems to do with Hopf-Galois structures. So the Greit-Paraygis theorem classifies Hopf-Galois structures on well, I'm using it on a Galois extension, but it's a bit broader than that, but it classifies a Hopf-Galois structure, which is sort of a package of a Hopf algebra and an action. So it's perfectly possible that you can have two different Hopf-Galois structures that involve the same Hopf algebra, or two or multiple actions of a given Hopf algebra on your extension. And they're well-known criteria for studying this kind of thing. Again, I think it's most natural to study this in the perm G kind of setting. So I actually want to think about N and M as being parked inside perm G, not as abstract groups, but actually G stable regular subgroups of perm G. So they're both G stable, the G acts on each of them. And in order for the Hopf algebras to be isomorphic, you require, well, it's equivalent to saying that there's an isomorphism from N to M that respects the action of G. So that you can transfer the action of G from one to the other. So G equivariant isomorphism. And it certainly is possible to translate this condition, this criterion across to the holomorph kind of formulation. I think my feeling on working with Alan on this, our feeling has been that it's a little bit less transparent to detect these Hopf algebra isomorphisms on the holomorph side. I think broadly it seems to be easier to work with the braces on the holomorph side and perhaps slightly easier to work with the Hopf-Galois structures on the perm G side. That's been our feeling. But it's certainly natural to ask whether we can detect or understand anything about these isomorphisms through the associated Skew braces. But as I was just saying, we at least like to work on the perm G side. So we needed to translate across the condition for two Skew braces to be isomorphic and understand what that looks like on the perm G side. And this, we didn't create this was already in the literature. And the condition is this. So two regular subgroups M and N parked inside perm G, they're going to yield the same Skew brace if and only if they differ by conjugation by some automorphism of G. So that's the sort of context that I'm going to work with for these next few results. So I'm thinking of N and M as being sat inside perm G. So just let me go back one slide, and seeing as the condition that comes up here is that M and N should be related by conjugating by some automorphism of G, it seemed that a natural place to start was to look at inner automorphisms. So let's imagine that G is non-abelian and look at what happens if I take a G stable regular subgroup and conjugate it by some inner automorphism. Well, by construction, well, I suppose the first thing to note is that I get another G stable regular subgroup, and by construction, M and N are going to yield the same skew brace. What can we say about the Hopf algebra isomorphism question? Well, it turns out in this case, the Hopf algebras that emerge are isomorphic as well. I think this is my only proof. I think this is, I was once advised that a talk like this should contain exactly one proof. So I think this is my only proof. So really the only smart observation in this proof is to write out the inner automorphism in terms of rho and lambda. So I want to write the inner automorphism arising from G as rho of G, lambda of G. And so when I conjugate N by this inner automorphism, what I'm really doing is conjugating it like this. And then if I use the fact that N is supposed to be G stable, then that means that I can absorb the lambda of G and the lambda of G inverse. That conjugating N by those just gives me N again. So really M is just N conjugated by rho of G. There's a section in my latest paper with Alan. We call these things rho conjugate subgroups, and you can then, that leads you to this idea of rho conjugate Hopf-Galois structures, which seem to be very, very close to each other. They share lots and lots of properties. Anyway, I end up being able to write M like this, and then there's a natural choice for an isomorphism from N to M. I just send an element eta to rho G, eta rho G inverse. And then if I examine what happens with the action, if I act on theta of eta by some element H in G, yet again, using the fact that elements of rho of G and elements of lambda of G commute with each other to get from that first line of the equation array to the second line of the equation array. And then going down to the third line there, conjugating eta by lambda of H is just the definition of H acting on eta, and then I can just package that back up and say, well, that's just theta of H acting on eta. So this map really does respect the G actions. I suppose I've just realized, I suppose I'm taking for granted here that M and N are actually isomorphic. I suppose that's I haven't actually explicitly said it, but it's going to be automatic. So you can squeeze a little bit more out of this. If you're in a situation where all the automorphisms of G are inner, then N and M yield the same skew brace. Sorry, if M and M yield the same skew brace, then the corresponding Hopf algebras are automatically isomorphic. And so that holds, for example, in my running example. If G is isomorphic to D3, then, and I start with this subgroup, this cyclic subgroup N that I've been playing with all through the talk, if I conjugate that by rho of something, I might get a new interesting regular subgroup. So if I conjugate that by rho of R, one of the generators of D3 there, then I get a different regular subgroup. That regular subgroup will yield a different Hopf-Galois structure, but it will have the same associated skew brace, and the acting Hopf algebra will be isomorphic to the one I first thought of. So it really is not very far away at all from the original Hopf-Galois structure. It's just a different action in there, but lots of the structural stuff is the same. But unfortunately, this doesn't happen very often. This is this sort of nice situation I've been describing, starting with inner automorphisms, really is pretty special. It doesn't take very long to run into less predictable behavior. So if you take G to be Q8, then there are 6 G-stable regular subgroups of perm G that are isomorphic to D4, and they all land on the same skew brace, but there are no G isomorphisms between them. So from a Hopf-Galois point of view, you've got 6 non-isomorphic or pairwise non-isomorphic Hopf algebras acting here, but from a skew brace point of view, they all land on the same skew brace. And then conversely, if I take G to be D4, then we can construct a large family of G-stable regular subgroups of perm G that are all isomorphic to D4 and are actually all mutually G isomorphic. So they even give the same Hopf algebra, but they don't yield the same skew brace. This idea of fixed point free abelian maps goes back to Childs and has been exploited by Allen and most recently by Lorenzo and Andrea Caranti, and it seems that it goes a long way. So these ideas of G isomorphism and brace equivalence that we set out to study don't interact in a particularly clean way in general, but they do give us 2 sort of partitions of the set of G-stable regular subgroups, or the set of Hopf-Galois structures, however you like to think about it. There are these different ways of identifying the subgroups, and there seems to be some mileage in kind of interacting these partitions in various ways. So there's some interesting interplay between them. So for example, if you start with a couple of subgroups that happen to be G isomorphic, then as you conjugate them by different automorphisms, the resulting subgroups are G isomorphic. So you can if you have a G isomorphism, then you can kind of relate that to other pairs of other isomorphisms by going through the skew brace. And similarly, there are interactions with the opposite construction where you might be able to bounce around a G isomorphism or bounce around a known fact about which brace a certain subgroup corresponds to and things like that. So there are these different ways of partitioning this set of subgroups, which we hope, we haven't finished investigating, can then tell us something about the corresponding Hopf-Galois structures by sort of propagating this information around. Anyway, thank you very much for your attention. I'd love to hear any questions or comments.